I'm going to talk today about the integral test. I gave us a little kind of teaser about this last time. The integral test. This is the first of several convergence tests that we're going to be talking about. A test for convergence. Convergence. And this, just like all of the different convergence tests, the integral test only works sometimes. It is only applicable to certain types of functions. And I'll tell you, this one works, you'll see why. This one works for decreasing functions. All right. And the picture you should have in mind is something like, and this is a picture that I drew last time, but I'm gonna draw kind of like three of them. This picture, come on now. Ooh, I got an arrow. I don't know how or why that happened. Something like this, right? This is like the graph of 1 over x. Although it doesn't have to be 1 over x. This works for any decreasing function. Now, this, of course, the area under the curve from 1 to infinity is that area right there. This area is the area under the curve 1 to infinity of, I'll just write this as f of x dx. The graph I'm drawing here is 1 over x, but it could be any decreasing function. They would all look more or less like that. Going down as you go to the right is what I mean by decreasing, all right? And you could draw also the Riemann sum using just the whole number endpoints. This Riemann sum here, continuing like that, right? Etc. This also goes on forever. But since the function is decreasing, these blocks, they get smaller and smaller as you go across. And the area of these blocks, the area here, the area of the blocks is the sum f of n equals 1 to infinity. All right? That's because the blocks each have width 1 on my picture here, and so their area is just equal to their height, and their height, the height of the first one is f of 1, the height of the second one is f of 2. So these heights, if you add them all up, you really do get the value of the series here from n equals 1 to infinity. All right? So now these are not equal. The area under the curve, the area under the red curve is not equal to the area of those blocks. Actually, because the function is decreasing, the area under the curve is straight up less than the area of the blocks. So this is a fact, and it's not only true in my example here, but since f is decreasing, this will always be the case. The integral 1 to infinity f of x dx is actually less than or equal to the sum n equals 1 to infinity f of n, right? Because the boxes that I drew, they stretch up above a little bit. All right? Yes? Could it ever be equal? Is that what you're saying? Yeah. Maybe it could not actually be equal. I can think of very weird examples where it might be equal, like for instance, if the red line instead of going down in a curve, if the red line actually looked like that, then the box area would be the same as the area under the curve. That's a very strange example, though. I mean, for ordinary functions, it would never actually be equal. But I think in theory, it is possible that they could be equal for some ridiculous example. It's not going to matter anyway, but yeah, that's a good question. Okay, and check it out. What about, as we do every time you think about doing a Riemann sum, here, what I did would be referred to as the Riemann sum using the left endpoints because these rectangles are hitting on the left side. What if we did the Riemann sum using the right endpoints? I'm going to draw that picture. So drawing the same function, but this time I'm going to draw the rectangles on the right endpoints. So here, this time each rectangle hits it on the other side, right? And again, because the function is decreasing, actually now you can say these boxes, if I add these boxes, their area is definitely less than the area under the curve. But these boxes here, if you think about how these work, like this, the first of these boxes has height f of 1, right? The second of the boxes has height f of 2 in the original picture. But in this picture that I drew here, they really are the same. It's only like this one, its height is f of 2. The next one is its height is f of 3, all right? So these boxes here, they are actually the same boxes. It's just you skipped f of 1. That's the only difference between the left Riemann sum and the right Riemann sum. When we're doing an ordinary Riemann sum, they also differ like on where they end up. They end up at two different places. But here we're going all the way to infinity, so there actually is no other difference. So anyway, here, the box area this time, the box area now is the sum n equals 2 to infinity f of n. I wrote 1, but I said 2. 2 is what I want to write, right? It's the same boxes, but you skip the first one. That's what I'm saying, if you use the other inequality. And this box area is now less than the integral. So this is actually less than, I'm going to say less than or equal, although really practically speaking, it's pretty much always less than, apart from some weird examples. All right. Those boxes are less than the integral. Okay, so in conclusion, I just said I have this inequality here and also this one here. Can we put them together? What you see is this sum is less than the integral, and then the integral is also less than this other sum. So putting those together, it says the sum n equals 2 to infinity f of n less than or equal to integral f of x dx from 1 to infinity, and that is less than or equal to the sum n equals 1 to infinity f of n. All right. What we have on the outside, those outside two things are really just like two different Riemann sums, and then the true area is in between them somewhere. All right. So, like I said last time, these things, the integral and the series are not equal, but they are related. And in particular, the value of the integral is kind of like in between this version of the series and this version of the series. And the only difference between this one and that one is just whether you include the first term or not. All right? What that means is, I think it's pretty clear to see, if the series diverges, like if this one diverges, then automatically this one also diverges because they're the same thing just except for the first term. But whether you include the first term or not doesn't affect if it diverges or not. So if this one diverges, then this one also diverges. That means automatically this one also diverges. Like the idea is, if this is going to infinity and this is also going to infinity and this is in between them, then it also has to go to infinity. All right? And if these two things converge, then this one also must converge. And this is the integral test. So the idea here is the one in the middle will converge or diverge along with the others. All right. The convergence of the one in the middle is the same as the convergence of the others. They don't converge to the same thing, but what I mean is, if the others converge, then the integral converges, and if the others diverge, then the integral diverges. All right. So here I'm going to write this as a theorem. We're not going to go through a proof. I mean, what I just explained is why it's true, but this is called the integral test. And it says, let me just make sure I get all the details right. First of all, this is only correct if the function is decreasing. And that's because this picture just won't work anymore. If the curve doesn't always go down, then actually some of these boxes will stick out above or below the curve, or whatever. You can't do any of this if it's not decreasing. So if f of x is increasing, decreasing. Sorry, that's what I said. Decreasing, and specifically, it must be decreasing on the interval from 1 to infinity. All right. I actually don't care if it's decreasing like on the other side of the y-axis or whatever. Like, this is all that really matters. If f of x is a decreasing function from 1 to infinity, then it says there's sort of two parts which say similar things. If the integral 1 to infinity f of x dx diverges, then the series diverges. And if it converges, then it converges. That's what I'm about to write. If the integral f of x dx converges, then the series converges. They do not converge to the same answer, but they either both diverge or they both converge. This is the integral test, all right? Sometimes when people are like saying this in some kind of a slightly informally, you could say it like the integral 1 to infinity f of x dx and the series n equal 1 to infinity f of n have the same convergence. Sometimes people say it this way, meaning either they are both convergent or they are both divergent. It doesn't mean they actually add up to the same answer, but it means that they either converge or diverge together. All right? This is called the integral test, and this is one way, if I give you a weird series, this is one way that you can tell if it converges or diverges sometimes. All right? It works when the function is decreasing. So what limits the applicability is it only works for decreasing functions, and furthermore, if you want to use this, you have to be able to find the integral, which that's also sometimes a hard step. But anyway, let's just try some examples. All right? Maybe I'll start with sort of two examples that we have already seen before. So let me just say you can use this to test if a series converges or not. And let me just say only for decreasing. Important to remember, if your series is not decreasing, then you just can't do this at all. But if it's decreasing, then you can do it. For example, here's a important example that we actually talked about last time. N equals 1 to infinity, 1 over n. This is called the harmonic series, and if you recall from last time, this diverges. And I gave a kind of weird argument about powers of 2. Although, it's actually a lot easier to demonstrate this using the integral test. So, let's, the question is, does it converge or not? The answer, we already know. It diverges, but let's see if we can do this using the integral test. All right? First of all, 1 over n is indeed decreasing, because when I do 1 over n with larger and larger n's, those fractions get smaller and smaller. So it's, I will just write 1 over n is decreasing. So we can use the integral test. All right? Sometimes I like to write integral test like that. 1 over n is decreasing, so we can use the integral test. So the question, does the series converge, is actually the same as the question, does the integral converge? And then that's an improper integral, and we already know how to do that. So let's try the integral instead. The whole point of this is that doing integrals is easier than adding up series. Even though doing integrals is sometimes hard, but this is what I'm talking about. I write it as an x just because I like to use x when I'm talking about continuous functions. And then let's just do the integral. So this is a pretty standard example of an improper integral. Of course, we have to begin like this, turn it into a limit, and then do the antiderivative. Anybody want to shout it out? What's the integral? 1 over x? ln of absolute value x. Great. And then I have to plug in 1 and t. This becomes lim t to infinity ln of t minus ln of 1. ln of 1 is 0, so that part doesn't matter. But ln of t, as t goes to infinity, remember the graph of ln looks like this. As t goes to infinity, this value does also go to infinity. So this right here diverges. All right. So the integral 1 to infinity, 1 over x dx, diverges. And therefore, but because of the integral test, that means the sum 1 over n equals 1 to infinity, diverges. All right, this is the power of the integral test. Any thoughts about that one? That's how we do the integral test, 1 over n. All right, let's try another slightly familiar example. How about the sum 1 over n squared? All right. One nice thing about the integral test is actually it'll tell you if it converges or not. So like even if you don't know if this converges or not, you can use the integral test and just work it out, and it'll tell you. So this one, 1 over n squared. Actually, this one we talked about last time also. This was calculated first by Euler. Anybody remember the answer? The answer is kind of ridiculous. But I said it last time. It's the answer is pi squared over 16, which the integral test will not tell you what the answer is, right? The integral test only tells you whether it converges or not. So, but anyway, 1 over n is decreasing. 1 over n squared is decreasing, so we can use the integral test. So I do the integral test. Instead of the series, I do the integral, 1 over x squared dx. And work it out and see what happens, right? 1 over x squared, of course, I'm going to write as x to the minus 2, and I'll turn this into a lim. T goes to infinity. Integral 1 to t. X to the minus 2, I said, with a dx, right? Do the integral, I increase the power by 1, so it becomes x to the minus 1, and I have to divide by minus 1, so I get lim t goes to infinity minus x to the minus 1. Plug in 1 and t. All right, these are pretty straightforward improper integrals. I hope everybody remembers how to do them. Minus t to the minus 1, and then subtract minus 1 to the minus 1. And what is this when t goes to infinity? You should be looking right here. T to the negative 1, what happens to that when t goes to infinity? Anybody say?
0.
Yeah, that's going to be 0, right? T to the minus 1 is 1 over t. Sometimes I have an easier time thinking about this lim if I write negative exponents really like as fractions. This, I suppose, is plus 1, the rest of it. And then that 1 over t becomes 0 when I do the limit. And so the answer here is 1. And so, converges. So, the sum 1 over n squared converges. All right? The fact that 1 is the answer here, I keep on saying this, I hope you're not sick of me saying it. 1 is the answer here, that doesn't mean that this equals 1, because the integral is not equal to the series. But it does mean, because this converges, it means this also converges. What it converges to is that's a completely different question, and very hard to answer in this example. It converges to pi squared over 6 for weird reasons. Or was it 12? Pi squared over 12, I think. Whatever. I don't especially remember these random facts. All right. This is the integral test. What about, can we just do one more of this type? What about 1 over n cubed? And then I want to generally make some conclusions in general about these kinds of things. You can see we tried 1 over n, it diverged. We can try 1 over n squared, it converged. What about 1 over n cubed? And then I think we'll be able to see some kind of a pattern. Again, 1 over n cubed is a decreasing sequence, so we can immediately set this up as an improper integral. I consider instead the integral 1 over x cubed dx from 1 to infinity. Right? It's very much like the one we just did. It's only, instead of a 2, it's a 3, right? So I am, again, going to convert it into a lim. We're going to do x to the minus 3 in there, right? From 1 to infinity. And this, when I do the antiderivative, from 1 to t, since it's an improper integral. When I do the antiderivative, negative 3 increases and becomes a negative 2, and then I divide by negative 2, so it's like minus a half x to the minus 2. All right. Plug them in. Minus a half t to the minus 2 minus a half 1 to the minus 2. And what do you say, converges or diverges? Converges, I think, is the answer. T to the minus 2 means 1 over t squared, and when t goes to infinity, that part becomes 0. All right? This is 1 over t squared right there. And so when the t goes to infinity, this here becomes 0, and the whole answer is just that, 1/2. Converges. All right? So, the sum 1 over n cubed converges. All right, the series converges because of the integral test. Can we say generally what's going to happen regarding will it converge or not, according to the exponent? I would say why this converges is because of, like, right here, right here, the fact that that's a negative exponent means I'm going to dump t down into the denominator, and then when I take this limit, it will converge. All right? In order for this limit to converge, it requires that this exponent be negative. So that is actually like the key little bit of information. It converges when this is negative. All right? The fact that that was negative means that when I write it again as a denominator, and then when I take the limit, it's going to, that part will converge. And of course, the other part is just a constant, so it'll converge. All right? It converges when that is negative. Can we say about the original thing, really the question that I want to ask is, for which p does the series 1 over n to the p converge? Right? We just did 3 examples of this type. P equals 1 made it diverge. P equals 2 and 3 were the other 2 that we checked, and those converged, right? Those were the 2 examples that we just did. You got an idea?
When p is greater than 1.
When p is greater than 1, it converges. Yeah, if you think about when p is greater than 1 here, that means when I write this as a negative exponent, it will say negative p, and then when I do the antiderivative, I add 1. As long as it's still negative, it will converge. And that, in order for it to still be negative, it means this number has to be like less than negative 1, which means the number p is more than 1. So it converges. Actually, I'm going to write the fancy math way. If and only if p is greater than 1, right? All bigger values of p will also make it converge, but p equals 1 diverges, and actually this is true even if p is a fraction or something. If p is a half, that diverges, all right? This is something that we should just remember. So I'm going to write this as another theorem. This is actually an important fact that will come up fairly often. So the sum 1 over n to the p, n equals 1 to infinity, this is called, there's a name for this, which in my opinion is kind of a stupid name. This is called the p series. In my opinion, this is a stupid name because p is just the name of that variable. But I mean, you can call that variable whatever you want. You could call it S, and then it would be the S series. This is a stupid name in my opinion. I don't have a better idea, but I don't like naming things after names of variables. Anyway, that's called the P series. I don't make the rules here. That is what it's called. And the important thing to remember is it converges if P is greater than 1, and it diverges if P is less than or equal to 1. That's the story about the P series. So 1 over n to the 1 diverges, but 1 over n squared or cubed or to the 4th, those all converge. All right. This is the theorem about the P series. All right, any thoughts about that? Okay, let's, I would like for you to try a couple. See if you can test for convergence using the integral test. Here's 2 examples. See how you like it. You should convert each to an improper integral and then try and do it and see what happens. That's your strategy. Okay? Yeah, that's good. You good here? That's looking good. Yeah. Kept it as an N. Because I usually make it X. Okay. Good. That's looking good. Okay here? Looks good.
Maybe you could actually play this do like into like that 3 times. Or no, I still have it.
No, that
One
one
right here.
Yeah.
Yeah, do this.
You want to close up too?
How's it going?
Can you do this or is that not legal?
It's not legal.
I think that's in the box.
Yeah, that's a little. That would have, when you make fractions like that, you would would be subtracting the exponent. So
Oh,
it
yeah,
goes
yeah.
negative 3 minus the inverse of it.
Yeah.
You don't need to do anything with it.
Yeah.
Just turn it into a good here? That's good.
Okay.
This one. Okay. Right here. Write those. All right. Yeah, so this is and then when he goes from 20, that is
The 1/3.
right. I would say right.
Right, no, just do it with right, so, okay.
Yeah.
Right. And then the next step. Yeah.
Again, yes, so
You have to get it from these columns.
these are numbers. It's got to be, yes, some value.
Nothing stays there, right?
Still good?
What do you negative 1/3, right? 1/3.
This one, it was in like a different format. It was like just ends.
I'll show you. Yeah, well, that's just.
Who's-
This one I wrote like a so.
All right, let's talk about them. So the first one here, you should do the integral. This is a slightly weird integral, but if you write as x to the minus 5 and then distribute, or you can think of as breaking up the fraction in some other way, this ends up being x to the minus 4 plus x to the minus 5, right? And now we do the antiderivatives on those. We just get two separate terms. 1 over minus 3x to the minus 3 plus 1 over minus 4x to the minus 4, plugging in 1 and infinity, and then this becomes lim, not infinity, t up there. We don't really plug in infinity. 1 over minus 3, t to the minus 3, which I find it a little easier if I write that way, and then 1/4 1 over t to the 4, and then subtract and plug in 1s. I'm just going to get some constants here, which I actually don't really care about those constants at all. Anyway, does it converge or not? It does converge. When you do this limit, each of those fractions with t's in the bottom becomes 0. So this is 0 minus whatever that is, and that converges. And it doesn't really matter what the number is, because that number doesn't really tell you anything. The whole point of all of this is just that the original series also converges. Just by looking, we don't know what it adds up to, but it converges. That's all I'm saying. All right, great. And the other one was e to the minus 3n. So I'm going to turn it into the integral e to the minus 3x. And then do the integral of this. This one maybe is an easier integral. I don't know. 1 to infinity. So this is lim t goes to infinity. The integral of e to the minus 3x is 1 over minus 3 e to the minus 3x. That's the old e to the kx. The integral is 1 over k e to the kx. And then I'm going to plug in 1 and t. Plugging in the t, well, I should write my lim. Plugging in the t gives me 1 over minus 3 e to the minus 3t, and then subtract 1 over minus 3 e to the negative 3 times 1. And then again, we have to find this limit. We don't actually care what the limit is, but just whether it converges or not. And as usual, I find it easier to write negative exponents as actual denominators. So e to the minus 3t, I'm going to write as 1 over e to the 3t. And then this part, I don't really care about. And then what happens now when t goes to infinity? What do you say, con or diverges? Con, yeah. Since t is in this denominator here, e to this, if you imagine sort of plugging infinity here, you get an infinite denominator, e to the infinity, something like that. So this is infinite denominator means this part is going to be 0. So that is, well, it's 0, and then I guess 1/3 e to the minus 3. Converges, though. That's all we care about. So that means, come on now, I've gone yellow. The series e to the minus 3n converges. That's it. The integral test works pretty well, in my opinion. It converts a series into an improper integral. And improper integrals, you know, they're not always easy to do, but at least they are possible to do, in much easier than just adding up the series by hand, which is sometimes going to be totally impossible. All right, great. That's all I want to say about the integral test. I'm looking at the clock like everybody else. We got 13 minutes remaining. Maybe I'll just say a few words about our next test. There's really not much more to say about the integral test. You'll have some practice with it on the homeworks for next time. But yeah, you just do it and it works. Only for decreasing functions though. All right, so the integral test works only for decreasing functions, and furthermore works only for functions which you are able to do the improper integral, which is, you know, some weird functions you won't even be able to do the integral. So more tests that work in other situations. The next test that I want to talk about, and there's actually sort of like a family of tests. These are called the comparison test, or tests. I'll write tests. The comparison tests. There's kind of like the ordinary comparison test, and then something that's a little fancier called the limit comparison test, and we'll eventually talk about both of them. But this is all about comparing one series to another one. If you have two series and you know that one is bigger than the other one, then this can tell you something about convergence of the one versus the other. So this is used when we can compare one series to another. And by compare, I mean using inequalities. All right? When we compare one series to another. And the idea is, if you have, so this is based on a very simple idea. I'm going to write sort of in kind of stupid language first, and then I'll write it like the sort of the real technical way as a theorem. But the basic idea is, if I have, you know, some kind of series, like a biggie series, which is bigger than a smalls series, as they say. If you have a big one and a little one, and you can write them using an inequality in this way, the bigger one is bigger than the little one. Check it out. Wouldn't you agree, if the bigger one converges, like if the bigger one is not infinity, then the smaller one also is not infinity, right? Because obviously you can't have the smaller one be infinity while the bigger one is not infinity, right? So the idea here is, if the bigger converges, then the smaller also converges. And for the same reason, and you have to keep it straight. Unfortunately, this can be a little confusing sometimes. For the same reason, though, if the small one diverges, if the small one goes to infinity, then the bigger one also has to go to infinity, right? because it's bigger than this other one. So if the bigger converges, then the smaller converges. And if the smaller diverges, then the bigger also diverges. All right? This is the idea behind the comparison test. Now, there are some caveats. What I said here is not always true, but this generally works when everything is positive. I was kind of encouraging you to only think of positive numbers. But of course, when we say diverges, this could mean either it like goes to infinity or maybe it goes to negative infinity. In which case, negative infinity is actually smaller than a convergent. So like, actually, if these are allowed to be negative, then it is possible actually for the smaller one to diverge to negative infinity while the bigger one converges, which would seem to contradict this right here. So it works when everything is positive. You have to be a little bit careful about the details here. So I will write the technical statement, and then maybe that'll do us for today. We will do a bunch of examples next time. So here is, I'll write it as a theorem. This is called the comparison test. And it says, if we have two series, well, let me just write it as two sequences. If an and bn are positive numbers for all n. So this is actually a fairly strong restriction, but most of the ones we've been talking about today have all been positive numbers. If you have negative terms, it messes up the comparison test. But anyway, if the an and the bn are positive for all n, then there are two things I want to say. If an is less than or equal to bn, and the sum bn converges, then the sum an converges. All right? So if the a's are smaller than the b's, and the b's are converging, this means the a's also are converging. And furthermore, the sum, like what it actually adds up to, is less than or equal to what the other one actually adds up to. All right? So if your individual terms are all less than the other terms, and the bigger ones converge, that means the little ones converge also, and what they converge to is less than or equal to what the other one converges to. All right? And so that's the first dot. There are two bullet points here. One is about if the bigger one converges. That's what I just said, if the bigger one converges. The next one will be about if the smaller one diverges, then that means the bigger one also diverges. So the next one will say also if an less than or equal to bn, and this time an diverges, I'm saying the smaller one diverges, then also the bigger one diverges. All right. So the first, if you were reading this informally speaking, this one here means bigger converges implies the smaller converges. And this one is kind of the other way around, and you have to just remember and keep it straight. The smaller diverges implies the bigger diverges. All right? This is called the comparison test. Really, it's kind of two different things together. All right? That's that. I think we will start off next time, after the quiz, of course, with some examples with the comparison test. See you later. Let me know if you want to talk about the homework. I'd be happy to chat.